Welcome to Air Academy Associates series on using SPC XL. In this video I will address the concept of correlation and show you how to obtain correlation coefficients using SPC XL. I will also spend a few minutes talking about the difference between correlation and causation and giving you some hints as to why when two variables are correlated, one does not necessarily cause the other. And we'll give you some examples of that. A basic definition of correlation that you might see in a dictionary is that of a relationship or a connection between two or more things. In data analysis, correlation examines how two variables or data sets are related. And we hear this all the time, how variables are related. Height and weight are correlated. Height and shoe size are correlated. Gas mileage on a vehicle is correlated to tire pressure. We've heard over many years how lung cancer and smoking are correlated. The Surgeon General now even has on packages that the warning that smoking causes lung cancer. Of course, that was a big issue with the tobacco companies who claimed correlation does not necessarily indicate causation. Anyway, there are different ways to measure the degree of correlation, but the most common one is Pearson's correlation coefficient, which is denoted by the letter R. The correlation coefficient R measures both the direction and strength of a linear relationship, and the key word here is linear, and we'll point that out as we go through the material here in this video. R has the following properties. First of all, it's a number between -1 and 1. It has a plus or minus sign, and its magnitude is between 0 and 1 inclusive. Strong positive relationships have R values that are close to 1. Strong negative relationships have R values that are close to a -1. And the weaker relationships tend to have R values that hover around 0. So, the next page and slide shows you some examples of positive and negative correlation. Positive correlation shown here on the left shows as you look at the X variable, that is the horizontal axis from left to right, you'll see the points in the Y direction going up to the upper right. That's a positive slope or gradient, and we call this a positive correlation when something like this happens. That is, as one variable gets bigger, so does the other one. Here is an example of negative correlation. Again, as this variable on the horizontal axis gets bigger, what happens to the variable on the y-axis? It gets smaller. There's a negative correlation. And then if you have one just kind of big glob of points, as I might call it, there's no correlation or no connection between the variables at all. Now let's put some numbers to the correlation coefficients. Let's see what kind of clustering we have about a line. The correlation coefficient, the magnitude of the coefficient, tells you how tightly clustered the points are around a line. That's that linear function again we talked about. And R here is about a 0.4, not very strong. Points are, spread out quite a ways beyond the line on both sides. Likewise over here, although the correlation coefficient over here is negative, and of course the correlation coefficient in the inner scatter plot is close to 0, if not 0. Here's an example of R equals 1. This is perfect correlation because we see that all of the points lie exactly on the line. Here's a correlation coefficient that is quite strong, 0.85. All the points are not on the line, but they're close to it, very close to it. And then, of course, here's another example of R equals 0. There's a rule of thumb for the strength of a relationship, and that is if the absolute value of R, that is the magnitude of the number without regard to sign, is at least 0.7, there's a fairly strong relationship. And as that number gets bigger to 0.8 to 0.9, that relationship grows stronger. And if there's a cutoff in correlation, in SPC XL, if you get a correlation coefficient of bigger than 0.7 in magnitude, it will show up in red. So it's very well pointed out, and that 0.7 is a very commonly used kind of cutoff for fairly significant or strong relationships. Here's an example of the correlation of skin cancer mortality versus latitude for each of the 50 states. Now, there are 50 dots there, and the line that goes through those dots is called the regression line. And that's the line I've been referring to, and you can look at the line and see that in this case it's a negative slope, so the R is negative. This is a fairly strong relationship between the latitude of a state and the mortality rate of skin cancer. Now, what is latitude again? Latitude is the northern or southern if it's minus, but northern latitude is the distance from the equator. So the points over here, this would be like states like Texas and Arizona, they are closer to the equator than states out here with a higher latitude like the North Dakotas, the Montanas, and the Alaskas up here. So you can see there's quite a relationship there, and of course we know that that relationship is fairly strong simply because, and this is where we get the idea that you're more apt to have skin cancer in the hot and more sunny climates. Now, the scatter plot is extremely important to get. Now, we have another video on scatter plots alone where the video shows the scatter plot and actually generates this regression line. This is a regression line. Regression is the methodology that is used to find the best line through the data. And these are 4 different data sets. They're called Anscombe's quartet. Anscombe came up with these 4 contrived data sets. They all have 11 data points. They all have the same R, or coefficient of correlation. And so, but they're completely different data sets. Notice this data set is much different than this one, much different than this one and this one. So they're all completely different. When we think of a line going through data, we kind of think of it like this. Now, there's a line that goes through this data too, but it's quite obvious this line is not the best fit for this data, which happens to be kind of nonlinear. A parabola would fit that better, and that's the purpose of regression. Again, the correlation coefficient is just about linear relationships. Here's a point, an outlier, clearly an outlier. If that were point were down here, we'd have the line probably going through all of the points exactly, and R would be 1. But R is 0.816 simply because of that data point. Likewise over here, this data point is an outlier clearly creating an R that's different than if this point were right in line with all of the other X's that are 8. That is, all the points had the same X value, namely 8. The software would not be able to calculate a correlation coefficient. And here's why. Remember what correlation is? As one variable changes, what happens to the other one? Well, guess what? One of the variables isn't changing. If this data point were right here, for example, the X values would not be changing. They'd all be constant. In a case like that, the software cannot print out a correlation coefficient. So let's stop here and go to the software and show you how to get these correlation coefficients. We are now in the software, so let's take a look at some data from the Space Shuttle. This is from the early days of the Space Shuttle prior to the Challenger accident, where the data was recorded for each launch. There were 24 launches prior to the Challenger, and temperature at launch and the number of O-ring failures were recorded for each launch. Let's see if there's a relationship between temperature and O-ring failures. So we come up here, we highlight the data, go to Sigma Zone. Here's our SPC XL main menu. We go to Analysis Tools, where you'll find the correlation analysis tool is right here under Analysis Tools, right there, Correlation Matrix, and you click on that and it says, is this the data? If you have not selected the data, you then do that. You need at least 2 columns of data or 2 rows of data. You can do columns or rows. You click on OK. Our data is in columns, and there is your correlation coefficient. Now let me blow that up a little bit bigger. It's a minus 0.56659. So that means as temperature goes up, the number of O-rings failures goes down. It also means as the temperature goes down, the number of O-ring failures goes up. It's not a strong relationship. It's a moderate. It doesn't reach that 0.7 threshold where this would turn red. Now we do have 2 red correlation coefficients here, but these are each variable or factor correlated with itself. I mean, if you tell me the temperature, I can tell you the temperature with 100% precision. So temperature is 100% correlated with itself, and so is the number of O-ring failures. But the cross correlation right here is about 0.56. And so kind of a moderate type of relationship. Let's go back, and now let's say we've looked at correlation coefficients up around 0.8. This one was around 0.5. Let's take some random data. Let's generate some random data using SPC XL. And we know that random data should not be correlated, right? So let's click on this discrete random number, and by discrete I mean whole numbers. Let's get 100 rows and let's say 5 columns, and the upper bound is going to be the number 10 and the lower bound is going to be the number 1. In other words, what I'm asking the SPC XL to do here is to generate 5 columns with 100 rows in each column, and the numbers that go into these cells are numbers between 1 and 10 completely randomly. Now I'm going to click OK, and here we have 5 randomly generated columns. It's 100 rows deep. I don't show all of those here, but you know what? We're going to get the correlation coefficients amongst all 5 of these variables, which we're now calling A, B, C, D, and E. So let's go to Analysis Tools and get the correlation matrix. This is why it's called a matrix. Data is in columns, and let's blow that up a little bit bigger. And you can see now that there's a bunch of correlation coefficients. That guy right there is the correlation coefficient between factor A and factor B. You can see it's 0.039. Not exactly 0, but it's down there, right? I mean, it's not different than 0. Factor C correlated with A has a 0.001. It's negative. Factor D with A has a correlation coefficient of 0.06, but positive. And, because it's random data, we would expect, we have 10 of these correlation coefficients besides the main ones, the ones. We have 10 of them, and about half of them have a negative correlation and about half of them have a positive, which is what we'd expect to see with random data. But the point I'm making is the magnitude of the numbers here are very small. 0.06, 0.06, 0.03, 0.01, 0.06, 0.02, 0.06. You see that they are very small. This is indicative of random data when you see correlations like that. Now that you've seen in SPC XL where to go to get correlation coefficients, let's talk and finish up a little bit about causation versus correlation. Let's take a look at a data set that I collected many years ago from a basketball scorebook at Air Academy High School. I knew the coach, and I said, "Coach, could I use your scorebook to gather some data?" He said, "Yes, as long as you don't use the players' names," which I have not done here. These are players 1 through 12, varsity, and I calculated or kept track of the cumulative fouls throughout the whole year. And this is over 23, 25 games or something like that, and the cumulative points scored. Now, if you plot that data on a scatter plot or get the correlation coefficient, it's big, it's strong, 0.87. There's a strong relationship between fouls committed and points scored. Now, clearly, one does not cause the other. If it did, we'd be coaching our players to go out there and foul more, because if they fouled more, they'd score more points, which is not a very good strategy, actually. So what's going on here? Maybe there's some other variable that's connected to both of these variables, namely fouls and points scored, that we don't even see on this chart. That's called a confounding variable or a confounding factor. And in this case, I think you could probably imagine what it might be. It's timing, playing time. How long did the player play? Obviously, when you play longer, you're going to typically score more points, and you're going to commit more fouls. And that's what we're seeing here. But a strong correlation. Now, the relationship is not really linear. A quadratic relationship would be a better fit. But remember, coefficient of correlation, R, gives you the linear relationship between the two variables. One last example is the famous example from Oldenburg, Germany, where the plot shown here is the number of storks observed in each of 7 years in Oldenburg, Germany, and the corresponding variable on the vertical axis is the city's population. So clearly there is a relationship between the number of storks and the population. Maybe that's where the old wives' tale is about storks bring babies. Well, probably not. So what's going on here? The underlying cause here is difficult to understand simply because you have to know what was going on in Oldenburg, Germany in those 7 years. It was a booming town, high, economic activity. People were moving to the city to get jobs, and of course when you move to the city, guess what happens? The city population grows. But what about the storks? Where are they coming from? Well, when people get jobs and they move to the city, they also build houses. Now the architecture of that time period was building houses with very steep gables, and the steep gables actually attracted the storks. So the underlying cause for this graph to look the way it does, highly correlated between storks and population, is you've got an interaction effect between the economy of Oldenburg, Germany at the time and the architectural style at that time during this period of 7 years. So interesting. You will see correlations, spurious correlations all over the place, but when you see it, don't jump to the conclusion that one variable causes the other. I hope this was a good summary of correlation and a little bit on causality. Thank you for watching.